topics covered in this video include atomic structure, orbitals, electron configurations, chemical bonding theory, valence bond theory, and sp3, sp2, and sp orbitals. So what is organic chemistry anyway? Well, it's the study of carbon-based compounds. Carbon is key because they form the basis of all living organisms. They make up the proteins in your hair, skin, and muscles. They make up your DNA, the foods that you eat, the medicines you take, the perfume you use, the dyes in your clothing, and a plethora of other things. And here are two examples of organic compounds that are medicines. Here on the right, we have the controversial oxycodone. And on the left, we have a medication, Lipitor, which is a statin medication used to prevent cardiovascular disease. Organic chemistry as a field has foundations dating from the mid-1700s when people isolated compounds from plants and animals. They typically were low melting solids that were very hard to isolate and work with. Originally, people thought that organic compounds had the same type of vital force as were in living things, and therefore they thought that you could not synthesize them in the laboratory. Of course, that turned out to be wrong. There were a couple key discoveries in the early 1800s. In 1816, Chevreul found that soap could be separated into several organic compounds, which he termed fatty acids. And then in 1828, Wohler showed that you could convert ammonium cyanate into the organic substance urea. So what's so special about carbon? Well, if you look at the periodic table, you'll notice that carbon is in group 4A. And of the more than 50 million chemical compounds known, most of them contain carbon. Since carbon is in group 4A, that means it has 4 valence electrons and can form 4 strong covalent bonds. It's also very good at forming bonds with other carbon atoms. And as a result, carbon is able to form a huge diversity of compounds. Section 1.1 reviews atomic structure from general chemistry. So you have the nucleus and then the electrons surrounding the nucleus. The nucleus consists of protons and neutrons. That's where most of the mass of an atom is, and it's teeny tiny compared to the total volume of the atom. Some key terms are atomic number and atomic mass and mass number. The atomic number, which is often referred to with a capital Z, is the number of protons in an atom's nucleus, and that is what defines an element. The mass number is the number of protons plus the neutrons in the nucleus, and atoms of a given element can have different numbers of neutrons. When they do, they're called isotopes. Now, the atomic mass, also called the atomic weight, is the weighted average mass in atomic mass units of an element's naturally occurring isotopes. That's the number that you see on the periodic table, typically underneath the symbol. Section 1.2 reviews the ideas of atomic orbitals. What is an atomic orbital? It's the mathematical solution to a wave equation, which unless you take an advanced physical chemistry class, you will never have to solve, but it tells us the location and behavior of a particular electron in an atom. Orbitals come in 4 flavors, s, p, d, and f, and in organic chemistry we'll primarily focus on the s and the p orbitals. Here are some cartoons illustrating what they look like. So the orbitals in an atom are organized into electron shells centered around the nucleus. And as you go out from the nucleus, those shells increase in size and energy. And different shells contain different numbers and kinds of orbitals, and each orbital can ever only take 2 electrons. So in the first shell, there's just the 1s orbital, and it could have 2 electrons. In the second shell, there's a 2s orbital, and there's actually 3 of these 2p orbitals. So you can get a total of 8 electrons in the second shell. Then when we move up to the third shell, we also have 3 d orbitals available. So as we go through each ascending shell, we add a new type of orbital, and there are 5 3d orbitals available. Again, 2 electrons per orbital. That gets us to a capacity of 18 electrons. For p orbitals, there are 3 of them, and the first time we see p orbitals appearing would be in the second shell, and we denote these different p orbitals as px, py, pz. The XYZ just refers to their orientation along the X, Y, and Z axes in three-dimensional space. Section 1.3 is a review of electron configurations from general chemistry. So the ground state electron configuration is a listing of the orbitals occupied by an atom's electrons, and there are some rules that we use. The first one is called the build-up principle or the Aufbau principle. And that just simply says you want to put electrons in the lowest energy orbitals first and then build up from there. The second rule is called the Pauli exclusion principle. That says you can only ever have two electrons in a single orbital, and when you do, they have to be of opposite spin. And then finally we have Hund's rule, which says when you're filling up the orbitals, you want to fill them up singly before you go back and pair up the electrons. So let's do an example. Give the ground state electron configuration for sulfur. So you may want to pause the video at this point, try this on your own, and then go forward. So here's the solution. First you look for the atomic number of sulfur, which is 16. I didn't say it was positively or negatively charged, so you assume it's net neutral. If an atom is neutral, then the number of electrons equal the number of protons. So therefore the number of electrons must be 16. Then you just start placing those electrons into orbitals, starting with the lowest energy orbital first and moving up. And this would be a visual representation where you actually draw the electrons as these arrows. And notice I have them going in opposite directions. That's a notation to indicate that they have opposite spin. The more concise way to do this would be to represent it in this way, where you have the number of electrons in each type of orbital. So in the 1s orbital, there's 2, hence we have a 2 here. In the 2s orbital, there's also 2 electrons. Then notice at the 2p, there's a 6. That's accounting for the fact that there are 3 separate 2p orbitals. 2 electrons per orbital gives us the number 6. So we don't write out 2p 3 times, because this is going to be a more concise notation. We just write 2p once, understanding that there are 3 of them. And that's how we can get 6 electrons. When we get to the third shell, we see that there are 2 electrons in the 3s orbital, and then a total of 4 electrons in the 3p type of orbital. Section 1.4 talks about chemical bonding theory. So Kekule and Cooper both observed that carbon is tetravalent, meaning that it has 4 bonds and that the bonds have specific spatial directions. In fact, they point out towards the corner of a tetrahedron. So here's a representation where this is carbon and these are the hydrogens, and notice they all point towards the edges of a tetrahedron. I could draw the tetrahedron like this. And when we're drawing structures, sometimes we use these solid and dashed wedges, and that's to indicate whether bonds are coming out of the page or into the page. If it's a solid wedge, it's coming out towards you. If it's a dashed wedge, it's going out away from you. And then if it's not dashed or solid, if it's just normal, like these, that just means that those bonds are in the plane of the paper. So why do bonds ever form at all? Well, they form because that results in compounds that are more stable than the separate atoms. And the electrons that are involved in bonding are the valence electrons, which are in the atom's outermost shell. Those are the electrons that are free to bond. Electrons in the inner shells are way too connected and attracted to the nucleus. They will not be involved in bonding. And there's 2 types of bonds, ionic bonds and covalent bonds. Covalent bonds are the ones we're going to be focused on in this class, and that's a result of sharing of electrons. Ionic bonds you probably learned about in general chemistry. That's where you've got one atom taking away electrons from a second atom. We can represent molecules using electron dot structures, also called Lewis structures, or bond line structures, sometimes called line bond, sometimes called bond line. I typically say bond line, also called Kekule structures. We're going to really be focusing on Friday on drawing these structures, and that's the main way we'll represent things. Putting in all of these electrons with the electron dot structures becomes just way too cumbersome when we start to represent larger and larger molecules. So this is what we're going to be using. So each line here represents a covalent bond. And then if you have non-bonded electrons, you represent those as dots. The number of covalent bonds that an atom will form depends on the number of valence electrons it needs to reach an octet, or a duet in case of hydrogen. So hydrogen has one electron, it just needs one more to get to a duet, so it likes to form one bond. Carbon, I mentioned it's in group 4A, so it's got 4 valence electrons, so it's 4 shy of the 8, so it wants to form 4 bonds. Nitrogen is in group 5A, so it has 5 valence electrons. It's shy of 3 to get to the 8, so it wants to form 3 bonds. Oxygen, do you notice a trend here? It's in group 6. It's got 6 valence electrons. It's shy of 2 to get to the 8, so it likes to form 2 bonds. And halogens, they're over in group 7, close to the right of the periodic table. They've already got 7 electrons. They just need one more to get to 8, so they like to form 1 bond. I call this my HAHONK rule, which I've made up. The HAHONK stands for halogens, hydrogen, oxygen, nitrogen, carbon, 1, 1, 2, 3, 4. It's just a reminder of the number of bonds these things like to form. Now, warning, this is only true for neutral compounds. If oxygen is negatively or positively charged, it will have a different number of bonds, as will nitrogen, and carbon, if negatively charged, will have 3 bonds. Also, an important thing here, carbon can never have more than 4 bonds, and hydrogen can never have more than 1 bond. The non-bonding electrons, also called often a lone pair, are those electrons that aren't involved in bonding, and we oftentimes represent them with dots on the atom that has them, but sometimes we omit them when drawing structures. And those non-bonding lone pair electrons are going to be important in reactivity that we'll talk about later in the semester. Section 1.5 discusses valence bond theory. So covalent bonds form when 2 atoms approach each other close enough so that they can actually overlap their singly occupied orbitals. So if we take the very simplest example of 2 hydrogen atoms, a hydrogen just has 1 electron and it's placed in that 1s orbital. You bring them close enough together, those 1s orbitals overlap and you form a bond. And the type of bond is a sigma bond, which just refers to the type of symmetry that it has. It's cylindrically symmetrical. This shows the amount of energy that's released. So if we have 2 hydrogen atoms by themselves, and then we form an H2 molecule, 436 kilojoules of energy is released. And another way of saying that is that HH, hydrogen, has a bond strength of 436 kilojoules per mole. So if you wanted to break the bond for 1 mole of hydrogen molecules, you would need to supply 436 kilojoules of energy. The bond length for any particular bond is the ideal distance between the nuclei that leads to maximum stability. If they're too close, they'll repel. If they're too far apart, they won't bond. And what's happening here is each hydrogen's electron is attracted to the nucleus of the other atom that it's bonding with. But if you get too close, then the nuclei repel each other. And if you get too far apart, well, then the nuclei aren't attracted to the other atom's electron. So there's this perfect distance that maximizes stability.